Let's look into the details of the Hafele Keating experiment from 1971. Hafele and Keating flew cesium atomic clocks around the world on commercial jet flights. One flight was eastward and the second one westward. When back, they compared the clocks with reference clocks left on the Earth's ground. The experiment proved again Einstein's time dilation predictions based on special relativity and general relativity. From general relativity, we know that a clock runs slower at Earth level and runs faster on a mountain or when climbing the height about 10 kilometers, like in an airplane. Here, the atomic clock runs faster than a clock left on Earth level. From special relativity, we know that a clock runs slower when having relative speed compared with a clock at rest. This effect describes the first formula on the left side. If the velocity v is not zero, the root gets smaller. This must be compensated by an increase of the corresponding time t index f. The increase of tick-tock of the clock means the clock runs slower with speed. The second part deals with the time dilation from general relativity. If we leave a g field while the radius distance increase, then the root value gets closer to 1, therefore compensated by the decrease of the time t index f. So the clock ticks faster on a mountain or in an aeroplane. Now to the details of the experiment. We are standing on the South Pole. The Earth turns clockwise, which means an eastward circle. In a first experiment, the jet plane goes with the Earth rotation, so flies eastward. The velocity v aeroplane eastward together with the speed of Earth rotation v0 defines a relative speed greater than the circle velocity of the atom clocks left on the Earth. Just the opposite if we look at the westward flight. Here the relative velocity of the propeller machine is smaller than v0. In short, the velocity v aeroplane relative eastward is greater than the velocity of the Earth rotation v0, and the v aeroplane relative westward is smaller than v0. What does it mean physically? During the eastward flight, the clocks in an aeroplane run slower compared with the clocks at rest. On the contrary, for the westward flight, the aeroplane clocks run faster here. Let us now come to the calculation of the special relativity time dilation based on an aeroplane's velocities. During the eastward flight at 8,900 meters altitude, we assume a constant velocity about 710 kilometers per hour. The flight time here is 41.2 hours eastward. During the westward direction, we assume 450 km per hour as an average, using a propeller machine for about 48.6 hours. During the eastward flight, the two clocks on board gain time, and during the westward flight, they lose time, based on the differences between the relative velocities. The calculation of the special relativity time dilation is standard. The root decreases with increasing velocity. So the clock time in an aeroplane increases due to the jet velocity, so the tick-tock periodic time slows down. We define such a slowdown by negative time difference. Thus, the eastward flight gives minus 182.9 nanoseconds, while the westward direction shows positive 97.5 nanoseconds. The accuracy from the approximation formula is very close to the standard formula given at the top. Time dilation due to velocity from the experiment within this table about minus 184 and 96 nanoseconds compared to the calculation minus 183 and 97 nanoseconds while using 700 km per hour and 450 km per hour respectively are in a very good agreement. Let us now discuss the general relativity time dilation aspect. The eastward flight with an altitude 8,900 meters and the westward direction with 9,400 height give nearly the same time dilation. Both flights result in a faster tick-tock of the aeroplane clocks. The calculation of the general relativity time dilation from the approximation formula are again in a very good agreement with the calculation from the correct formula. Insofar as both directions lead to a faster ticking aeroplane clock, both values are positive for that. Eastward, we have 144.1 nanoseconds and westward 179.5 nanoseconds. All in one table shows a very good agreement from the general relativity time dilation comparison between calculation and experimental data. The chosen average velocities for eastward and westward flight fits the experimental data very good, although Hafele and Keating do not give such average values. Of course, they use the velocities they measured continuously during their flights. The next question is based on the correct formula while also including the influence of the Sun's G-field, influencing time dilation at Earth level and aeroplane altitude. The mean distance is about 1.5 million kilometers. During a night and day session, we change the distance about 12,000 kilometers. So what's about the contribution on the atomic clocks within the Hafele Keating experiment? Here we have the time dilation formula from general relativity while using Schwarzschild metric. The formula on the right is based on GR combined with thermodynamic principles, my private theory. If you like, see ResearchGate for more details. The parameter A is from Higgs, W, and Z boson additional vacuum interaction, not discussed within general relativity before. This table shows the results from the calculation while using the GR formula defining a number set index f and defining a set index A number, including the new tiny parameter big A. As I said before, a contribution given from GR combined with thermodynamics. As we can see, the influence of the Sun's G-field derived from set index A numbers is small, but today's atomic clocks might register this effect, as well as a minute difference between day and night session, first and second lines. By the way, the difference between set index F without Sun and the number set index A 0 indicate the tiny contribution from the new parameter big A. At least I like to mention a possible experiment for to test a day and night session influence, combined with a new parameter A from GR plus thermodynamics. One atomic clock on a mountain, 1,000-meter height, and a second clock -1,000 meters down into a mine. I like to leave the results for your own interpretation, but to let you know, Z is the calculation without Sun influence, and ZA includes both Sun influence and influence of the tiny parameter A.